Hi, I'm Dick Seitz. Welcome to the Software Screw Up series. Today's episode 4 is about code oversight. Oversight in the sense of overlooked mistake. So you all know about the dining philosophers with the 5 philosophers and 5 forks, and they need 2 forks to eat. But do you know about the drinking philosophers with the 5 philosophers and 1 pitcher of beer in the middle of the table? The drinking philosophers don't have any mugs, so they all just grab for the pitcher. Whoever gets it hangs on to it, drinks from it, after a long time perhaps eventually puts it back, while everyone else is waiting impatiently. And then of course it repeats. You go around and everybody, as soon as the pitcher's back in the center of the table, everyone grabs for it. So people who are slow off the mark might be thirsty for a long time, or worse, people who doze off, go to sleep. By the time they're woken up hearing the beer hit the table again, they may be much too late to actually grab the pitcher. It's the same with software locks. When you have a software lock for a critical section, the simple design is all the processes that want the lock grab for the lock, and whichever process gets it holds onto it while it's doing the critical section work, which could take a while, and then eventually puts the lock back, and then repeat, and everyone grabs for the lock. And so whenever a process is holding the lock, everyone else is just waiting impatiently. Here's a real example from 2009 of holding a lock much too long. There was a routine called RPC stats that its structure is like this. It would acquire a lock on a large data structure, allocate a buffer, format that data structure into the buffer as a web page, so lots of text formatting, and then test if debugging was on, and if so, it would print the buffer, and then it would free the buffer, and then it would release the lock. Most of the time, debugging was off, so the actual flow through the routine was lock the data structure, allocate the buffer, format all of the data structure into the buffer, don't do anything with the buffer, free the buffer, release the lock. And that had the effect shown in this sort of diagram of everyone who's trying to use the data structure gets locked out while this weird RPC stats routine is formatting a web page that no one ever gets to see. The effect was that there were occasional times when RPC data structure got locked and new remote procedure calls couldn't start for milliseconds. And no one quite knew why until we spent a long time discovering where the lock, what the lock was, and who was holding it. So then we did the quick symptomatic fix, of course. We moved the tester debugging up to the front so that if we aren't debugging it, it can return immediately. That got rid of the immediate problem. But whenever the people who were in charge of running the data centers, the system reliability engineers, actually turned on the debugging flag in order to track down what was going on in some machine that was running slowly, then we went back to locking out all of the remote procedure call tasks while all this formatting was going on. So the longer term fix to do the real fix was to acquire the data structure lock, quickly make a binary copy of the data structure and release the lock. Then spend lazily allocating a buffer, formatting the copy into the buffer as a web page, and then printing it and freeing the buffer. So that reduced the locking time by about a factor of 1,000 from milliseconds to microseconds. This example, this diagram is not from that example. I don't have any trace of the 2009 work, but you can see how just doing the copy and then everyone gets to go on makes a huge difference. If we go back to the drinking philosophers, well, if you have mugs, then they can have a much better dynamic. They all grab for the pitcher. Whoever gets it fills their mug and then quickly puts it back. Then can drink their mug at leisure. Meanwhile, other people are grabbing for the pitcher, filling their mugs and putting it back. And that makes a huge change in the dynamics and a huge performance difference. However, you need to keep in mind that random lock grabbing is always subject to starvation, even if the odds of starvation are fairly low. So in a robust production design, there's always some form of waiting in order queue, like you would find, the traditional bakery numbers. So everyone waiting gets a turn, and any lock holder has to go to the back of the line before they can grab the lock again. So that's today's episode. Thank you for listening to the Software Screw-Up series. Take care.